about that, please? Any question? Any question? So here the integral equation for circulation. Here is the integral equation for circulation was this guy. It's different from Tudorson and von Karman and series because this is over -1 to 1, over the plate, not over the wake. And where it came from this equation, which is the no penetration boundary condition. Okay? So this is actually the no penetration boundary condition. Any question? The loads here and the loads there are non-circulatory and circulatory lumped together. Okay? But over there you have them separate. Any question? So, I mean, I will not test you here on this stuff, but this is important for you to know how to develop your model anyway, if you will ever do. Let's finish here. I mean, we have some time, and I need this time. Actually, I may take a few minutes more today. It's hopefully to finish what we want. So let's look at the thin airfoil theory. Do you have any question, please, before going to the thin airfoil theory? Any question?
So will we return to the thin airfoil theory again?
Kind of. I will extend it to the unsteady version of it. So I'll just remind you of the thin airfoil theory. So what do we have? Actually, I draw this too many times today. So anyway, you have your gamma bound, right? Function of x. And maybe your airfoil. So we have a camber here or whatever. So we have this guy is moving with u infinity. So the normal speed due to gamma is equal to the normal speed due to motion. This gives you the well-known equation 1 negative 2 by negative b to b gamma bound of whatever zeta d zeta over x minus zeta equals to the negative u infinity alpha minus d camber if you have a camber by dx. Okay? This was the integral equation for circulation. It's steady. This is the steady thin airfoil theory. Steady. And please, if you have a question, stop me, please. As you see, this is the no penetration boundary condition. Immediately gives you your governing equation. You don't have anything more. You can apply Sohngen inversion formula if this is a nice function. If it's not, what did we do if you remember? Do you remember how we solved this? How we solved this?
Series solution.
Very good. We assume that this guy is 2u a naught tan phi over 2 plus summation an sine n phi. So if you plug this formula here, remember x is x and phi, x is b cosine phi. If you plug this formula here in your equation, governing equation, you get the no penetration boundary condition, but in this form. So a naught plus summation an cosine n phi equals the same thing divided by u naught. So this is actually the v motion, right? So v motion divided by u infinity as a function of x or function of phi. So this was so easy. When you assume gamma bound is your unknown distribution. When you assume the form, okay, we assume that the function dependence, but with unknown coefficients. So I need to determine the coefficients. when you substitute here, you get this equation. Hopefully this equation can tell you how to determine the coefficients, and it does. How? Because if you have any given function, remember this is given, if you have any given function, I can represent it in a cosine Fourier series, and you can get the coefficients. So this is simply the cosine Fourier representation of this guy. So I can get A0, A1, A2 by these integrals. We're done, okay? And once you did that, your gamma, which is the integral of gamma, little gamma, turns out to be 2 by UB, just depending on A0 plus A1 over 2. For a rigid airfoil, it's the 3/4 chord. That's okay. And more importantly, that the CP, the pressure distribution at any x, it was 2 gamma divided by u. So if you integrate this guy to get the lift, it's as if you're integrating this guy to get gamma. So this is why the lift here in the steady flow simply rho u gamma. So this gives you that CL is 2 pi, the same things, depends on the exact same coefficients, the exact same way. Okay? Any question about that? So this was just the Airfoil theory that we did before in detail, and you were tested upon it. And what if we have the unsteady version of it? What changes? So, first of all, you already know that we need to add weight, right? So this guy is gamma here, that's okay. It's function of x and t now. And we need to add weight. Gamma weight, that's function of x and t. It's the exact same equation. So same, of course, it's just the definition of the non-penetration boundary condition. V normal due to all the gammas, now it's gamma bound and gamma weight, is equal to the V motion. So this equation will look like this, negative 1 over 2 pi, gamma bound, Z and T, x minus zeta, negative 1 over 2 pi, this is the problem here, because I'm introducing a new unknown, right? Gamma weight of zeta d zeta over x minus zeta equal to the same right hand side. So I'll call it V motion. Of x and t. Okay? Negative b to b, this guy is from b to infinity. That's okay. We will do the same thing. Remember now this is a new unknown, so we will do the same thing. So we will use the exact same thing. So gamma b of x, which can be replaced with phi, but now it's a function of t. So this is 2u a naught tan phi over 2 plus summation a n sine n phi. These coefficients are no longer constants, they are functions of time, right? Okay? Makes sense, that's okay. But it's the exact same form, so if you substitute here and integrate over zeta, which is phi, you will get the exact same result. Yes, so you will get a naught, it's just a function of time, plus summation a n cosine n phi, plus the stuff coming from the wake, equal the V motion on the right hand side. Okay? Any question about that? So this is the problem, is that you have unknowns here. You have unknowns, and this is V motion divided by U infinity. So what Peters did, Unsteady theory and Airfoil theory goes before Peters, but he made very significant contributions. This is Peters, 2008, so it's relatively recent. We were talking about 1914. all of a sudden it's 2008. I guess he has also a paper on similar stuff from 1995. But the one that is more complete and detailed is 2008. Maybe with a little bit different spirit. Anyway, so what he said is that this guy will assume the same form. Assume that, what's this? What's this as a whole? What's this? Well, this is the velocity, the down velocity at a point x due to the wake, right? So this is the down wash due to wake. He called it this is a function of x, right? He called it lambda of x. And because we're dividing by u infinity or u naught or u whatever, so lambda over u, you will represent the exact same form here. He said, okay, I can represent, it's a function, I can write it whatever I like. So this is lambda naught plus summation lambda n cosine n phi. And let's look at this equation and see what is known and what is unknown. Before we had this guy, the right hand side is completely known. I can represent it as Fourier cosine, get coefficients. Its coefficients is the exact same coefficients, right? Doesn't see it. Over there, again, this is known. I can represent it in a Fourier cosine, get coefficients. But these coefficients, every coefficient will correspond to addition of 2, right? So let's assume this to be b naught plus summation bn cosine n phi, okay? So b naught, for example, what is the relation between ai, lambda I, and bi? It's this relation, right? I mean, we're just equating coefficients, it's nothing more. Can you tell me here in this equation what is known and what's unknown? What is known? What is known here? No, AI are the coefficients of gamma bound. Gamma bound is unknown. I have no means so far to get it. The same for lambda. BI comes from the motion. I know the motion. So the right hand side is known. The left hand side is unknown. Okay. So that's okay. So just keep this in mind that we have no means directly to get the coefficients of the bound circulation. Unlike the steady case. So we need additional information. Of course, because so far, what did we do? So far, we just exploited the no penetration boundary condition. By itself is not sufficient. We need conservation of circulation of the law or the Carter condition, something more, right? It's an unsteady problem. So this is just a manifestation for the no penetration boundary condition. It's not sufficient, we need more. Over there it was sufficient, completely solved the problem. That's okay. But why still we didn't see why the left is not rho gamma anymore? Okay, let's see. Let's see it here. Well, the bound circulation, it has the same coefficients, exactly same coefficients as here. So if you integrate it to get the total gamma, it's the exact same thing. So your gamma bound is the exact same thing. Negative b to b gamma bound of x and t dx, this is function of t, this will be the exact same thing. 2 by u b a naught plus a 1 over 2, that's fine. I'm sorry, it's not. Yeah, that's right. A naught plus a 1 over 2. But a naught plus a 1 over 2 is not directly related to motion, right? It's not directly related to motion like here. They are motion minus the weight. So this is 2 by u b b naught plus b1 over 2. This is motion, this is known. For a rigid airfoil, this is angle of attack at 3/4 cooled, minus lambda naught plus lambda 1 over 2. This is downwash due to the weight. It's not, it's unknown. Okay? That's okay. And here is the problem. So let's look at delta Cp. Well, we had this relation before. What is the relation between pressure and gamma? Here it is. So please copy this for me. So the delta Cp I will divide by 1/2 rho u squared. Okay? So let's write this. So delta Cp, the unsteady Bernoulli now, it's not the steady Bernoulli. Delta Cp at any x is 2 gamma at the same x divided by u. And it doesn't make sense if we're in the way, well, yeah. Plus partial t term, 2 divided by u squared, partial t integral from negative b to any x, gamma b of x dx. You can see it immediately now. Over there in the steady case, the Cp at any x is just related to this gamma, to the circulation at the same x. So if you integrate both to get the total lift and the total circulation, they are just proportional, right? Here, because of the unsteady term in the Bernoulli equation, d phi dt, partial t, this guy is related to the same here plus another term. So, when you integrate, you will not get the same result. Here is, when we integrate to get the CL, it's 2 pi, it's B naught plus B1 over 2 alpha 3/4 minus lambda naught plus 1/2 B2 dot minus B2 dot over 2. This is what you get, I mean, just by direct integration, this is what you will get. So, let's look here. This is the total lift. There is no division here between circulatory and non-circulatory. So we need to extract here the circulatory and non-circulatory. And this is what the pioneers decided to do from this point of view. They said, well, I mean, look at this. Let's review together. B's are the motion, the velocity of the airfoil. So B dots are what? Acceleration terms, right? So it's convenient or makes sense if you define this to be the circulatory lift, and this is the acceleration terms. This is what everybody did. This is what Tedorson, von Karman, Sears, Wagner. This is the definition of the circulatory lift in Tedorson formulation and Wagner formulation. So it's B naught B1 over 2. Angle of attack at the 3/4 minus lambda naught. What's lambda naught? Lambda in general is the downwash due to weight. The downwash due to weight. If this is the plate and you have a vortex here, it creates downwash, right? And this downwash has a distribution, it's a function of x on the plate. Lambda naught is the first term of the Fourier representation. It's the average. Okay? The average downwash. And these are acceleration terms. So interestingly, these are known, right?